Okay, welcome again to another video in our series, and today we're going to be kind of taking a detour. We're going to be talking about a singular problem that occurs in digital design everywhere, not just VHDL, but in any digital system, and that is how to deal with problems associated with asynchronous inputs. And the main problem that we're going to be talking about is called metastability. So let's kind of get an idea of what metastability is and how it affects your design and what causes it. So the idea is fairly simple. You have an input that comes in and it's an unpredictable input. Let's say a switch input in your design where a user could be pushing a switch as a way to interact with the system. The user can push the switch at any time. You have absolutely no control over when that happens. And so if you're in a synchronous system, that can matter a great deal. Basically, if the user inputs the data at the moment that the system is sampling the data, then it may not be a high or a low at that point. If you think about it, as you push the button, you're going to be getting a transition from a low to a high, or a high to a low, depending on how you've hooked up your button and how you're interfacing it. But that transition could be in the process of making the transfer from high to low, or from high to low, or low to high, and then the input is sampled by the clock. And so when that happens, what is the input? Is it going to be a high or is it going to be a low? Well, we oftentimes think of digital systems as being a binary system, and they are. They actually either favor a high or a low state. But we also are dealing with an electrical system here, because it's not just ones and zeros. This is current and voltage. And so all of the electronics that factor into this, such as the capacitance of the input, the rate at which the signals can change, all of that has an impact on it. How frequently you're sampling, in other words, your clocking frequency, will have an impact on that as well. And so if that happens, it results in an unstable output for a short period of time. And that's called, that's what we talk to as metastability. So this is a graphic that's oftentimes used to show the idea of metastability. So think of the dot that's positioned here. Think of this dot as being your input, okay? So if your input comes in at a low voltage, right? So if the input is within the valid low range, it will drop and fall into the proper range for the output. So it'll know immediately that, oh, this is a low input. That's fantastic. Now remember, we're talking about a system where we have a D flip-flop. So the D flip-flop is sampling the input on the clock edge. So the clock edge comes in, it takes whatever's on D, passes it through to the output Q, and that's how the flip-flop's supposed to work. What we're talking about is that situation where when the clock edge comes, the input is in transition. And so it may sample in the middle of that transition. And that could create this bizarreness to us, right? So if it samples a low, then the output will be low. If it samples a high, then the output will be high. Well, what happens if it samples in between? And this can be represented by this little graphic here. You see we've got a curve here. This is sort of an analogy of dropping a ball on a hill, okay? So think of taking a ball and you're dropping a ball on top of a hill. Now, if you're closer to this side, the ball will hit and then roll down and eventually reach the proper state of low in this case. But there will be a delay. And so the output will be unstable for a certain period of time, right? Based on where it hits. So if the ball hits here, it will roll down here, but there's a delay. There's a time delay before it actually gets stable, and the output can be in an undetermined state. It will not have gone high or low, and in fact, it will be unstable. The worst possible case is when the ball hits right in the middle of this, which could result in a long time of it sitting here and then eventually rolling down to one side or the other, depending on lots of different conditions. Now, the bottom line here is that it will eventually stabilize, right? And so that's one of the ways that you can handle metastability, is recognizing that it'll eventually stabilize to one state or the other, but it will take some time to do that. All right. So basically, with that in mind, let's see what this looks like from a signal point of view. So if we take a look at a signal that's coming in, and let's particularly look at, let's say that this is our clock. So this is our clock edge, okay? And if we're talking about a D flip-flop, basically we consider remember, the edge is not perfectly straight. No signal changes in nature go from immediately low to high and high to low in an instant, right? There's a ramp, there's a rate at which it rises or falls to the appropriate level. In this particular case, we tend to measure from the middle, 50% point, voltage point, of when that edge is there. And then we specify two parameters. We specify a setup time, okay? So we specify a setup time. And this would be our setup time. And then we specify a hold time. And this would be our hold time. Okay, so this is a specification that all synchronous elements will have. The setup and hold times are basically a criteria that you must meet for this to perform properly. We must make sure that the input is valid prior to the setup time. So we're trying to make sure the input is valid prior to the setup times time duration here. So in other words, if I'm going to put something into the flip-flop as data for D, I need to make sure it's stable before this time duration related to the clock edge. So right before the clock edge, it has to be there. Same thing for the hold time. The hold time represents the time, the expected time for you to hold that signal consistent without changing it after the clock edge. So you have to make sure the system is valid just before the edge and a little bit after the edge in order for it to work properly. The problems come when your signal is inside that range. So if your signal is inside this range, that's where the problems come. So an invalid input then would look something like this, where you're not quite at the right, you haven't quite stabilized yet in this range, and then that would create this metastable output, the output that's not quite high, not quite low, and can create some real problems in your design. This is an example here of a high input that is valid, because notice during the time duration that we're talking about, it's a high. This is an example of a low input here, because during the time duration between the setup time and the hold time, the signal is a low. So it's a valid throughout the whole position. The reason this is invalid here is because it's neither high nor low in that interim period, and that's where the problems come in. Now, obviously, we've exaggerated the slope here. Most systems have a fairly quick rise or fall time, but still, in the nature of inputs, you can't predict when somebody's going to push the button relative to your clock. And that means that you have to account for the possibility that it may happen at some point. So there is a chance at some point that the input is just not going to be there at the correct time. And so your design needs to kind of take that into consideration. All right, so we're going to be looking again at what this looks like a little bit closer from the standpoint of the inputs and the outputs. So if we look here, we'll see here's our clock edge again, right? Here's the invalid input. So this is another invalid input, because in that range of setup and hold time, the signal's still changing. What will the output look like? Well, this is just a sample of what it might look like. It really varies. I mean, it varies on the type of technology that's being used in the chip, the capacitances associated with that particular input. Lots of factors figure into it. We're going to look at an equation that describes that in a minute. But this is the problem. The output then becomes unstable. So for a short period of time, the output is undefined until it finally settles into another output. Now that's the problem. If you're using this signal, so if this signal here is being used in the rest of your design and it's unstable and you sample it on the next clock cycle, then you've got some problems, right? Because what's it going to be? And if your system is a digital system, a synchronous digital system, having an invalid input or having it be misinterpreted can really cause the system to break and not function properly. It's like you expect a 1, but it gets a 0, or you expect a 0 and it evaluates to a 1. That can wreck your state machines. That can wreck all of the systems and cause your system to act in an odd and strange way. So what are we going to do about that? Well, first off, let's take a look at there is a analysis that goes on. The chip manufacturers and other things put a lot of time and effort into looking at their inputs and establishing the best possible reduction in metastability problems that they can in the design. And they use this equation as a guiding example of how to do that. So when we talk about metastability, you always hear the term MTBF, which is the mean time before failure. And this is a measure of how long you expect this to fail. Obviously, this is not something that's going to happen frequently. In fact, mean time to failure tends to be measured in terms of years, right? It's 5 years for this to fail or something like that. The problem is if you're dealing with a super sensitive system, let's say it's a medical monitoring equipment, and you're using a medical device to monitor somebody who's in serious, you can't really afford to have this thing mess up on user input when they're typing and stuff and trying to get systems to take care of the patient, right? So you can't have this thing failing in the middle of taking care of a patient. And so we want a very, very high mean time to failure so that the chances of this are almost impossible, like hundreds of years or something. If you can get that up there, then that's going to be something you want to try to do. And there are techniques that we can do to help improve that, but you can't ever prevent this, right? So it's one of those things that can't be completely prevented, but you can make the odds of it happening so low that it's likely never to happen, right? Sort of like we could get hit by an asteroid, but the odds of that are so low right now that we don't necessarily have to worry about that in every day-to-day life. This is the equation that describes the mean time before failure. And then basically this is something that we can see how different aspects of the circuit can affect it. There are two capacitances associated with the mean time to failure. The one thing that we need to recognize is the exponential component in the top part of this. So obviously, with the exponential component, we're going to see a pretty sharp rise if we can cause this term to increase. Then we can see a fairly large rise in the mean time before failure. Okay, so there's lots of techniques that the designers of the chip can do to make this happen. If they can reduce, for instance, if they can reduce the capacitance here, then that will increase the term and cause the mean time to failure to get larger and larger. That's a good thing. But we don't have much control over that as designers. So that's really a designer of the chip. That's how they make the chip and design it. And the manufacturers work very hard to keep those terms very low indeed. Now we can affect the frequency, the clocking frequency and the frequency at which the data changes. But that's really not something we want to really play with too much, because we're trying to get our devices to work faster and faster, and as they get faster and faster, that becomes a factor. But the thing that we can really affect in our design, right? Because we want our device, we don't want to use the frequency as a determiner, because we're trying to get our designs to work as fast as possible. What we're really trying to do is get the this term up here to grow and get as fast as possible. So with that in mind, if we focus on this term, which represents the available settling time, then if we increase the available settling time, that will have a pretty significant impact on increasing our mean time before failure. And so that's the technique that we use in digital to prevent this. So basically what we're doing is we're saying we're delaying our use of this signal by a certain amount in order to ensure that the metastability problem works itself out before we sample it again. So that's basically the bottom line. So if we can get that term higher, then that's going to improve our performance. Obviously, the higher the frequency of our system, the smaller this becomes, and that works against us. But like I said before, we're constantly trying to make our systems run faster and do better, so we don't really want to hurt that too much, although lower frequencies do give us better performance as far as the mean time to failure. We really can focus on this this time for settling time. Okay, so how long it takes for this to settle. So how would we do that? Well, the way in which we do that is we use this thing called a synchronization chain. And a synchronization chain allows us to take the input and chain it through a number of D flip-flops. So if this becomes unstable, if this area here becomes unstable, it's still not going to affect the end design because it will finally stabilize, and then we sample it again, and then we have a stable output. Right? So that's the whole idea. If we can delay this enough, if our characterizations can be enough delayed, then this is a good design. On a really critical system, you might, instead of using 2 flip-flops, you might end up using 3 flip-flops, okay? And so the three flip-flop solution gives you even significantly more. So remember, this is an exponential function. So even doubling the time will have a significant more, you'll get more than twice the mean time before failure for that. So this is where we're heading. This is how we handle the situation in digital design. And I've got an example here of how to do this in a process. We've got a process called sync chain here in which we implement this very design. So we're going to implement this exact design in this particular process. And the idea is we have a chain of 2 D flip-flops, and we have named these things appropriately here to make them clear. So we've got our asynchronous input, and our asynchronous input basically feeds into the first flip-flop. Then we have an unsafe output coming there, and then we have our safe output coming off the second one. So we can easily describe that in VHDL in very simple terms. Basically, we have an internal variable that represents the unsafe output, and then we come in here and we say, all right, if reset's active, we initialize the signals. But here's where the real work occurs. When there's a rising edge, we transfer the unsafe to the safe output. Okay, so that's this one here. Sorry. That's that one there. And then we transfer the asynchronous input to the, and that's this one here, to the unsafe output. So we're really simply doing a D flip-flop, but a dual chain. You can expand this to a 3 chain if you wanted to, so that you have 3 flip-flops in the order. And the more you do this, the more certain you are that you're going to likely not have a problem. I think in most designs, especially in the modern VHDL, most of the people that design the modern FPGAs, I mean, we have very, very high mean time before failures already. So the chances are really small already. But if you're doing a medical system or anything like that, then you definitely want to create a synchronization chain. The longer your synchronization chain is, the more you're going to have, the less trouble you'll have with metastability. But remember, the longer your chain is, that's the delay in which it's going to be before the input sees your signal, right? So if you're having a signal come in to this side, it's going to take 2 clock cycles for it to get to this side. So you've delayed the signal by 2 clock cycles. You put in a synchronous chain of 3, you're going to delay the input by 3 clock cycles, etc. So the longer your chain, the more delayed the input is. Now that may or may not be a big deal. Typically with asynchronous inputs from a user, like a button or something that somebody's pushing, that's irrelevant. Because the time it takes to scan through that is faster than the human would notice any response issues. The other application of this idea, though, is when you're mapping 2 different clock domains. So if you have 2 clock domains in your FPGA, now we've talked about this before, mainly in this course we've said this is a bad idea. We're just going to have 1 clock domain and we're going to go with it. But there are cases where you want to have 2 different clock domains, whether it's for power consumption reduction, or maybe you have 2 independent systems that just need different clocks for whatever reason. You might need to communicate with those, bring those 2 together. And so in that case, when you're taking 1 clocked system and interfacing with another, that's really an asynchronous thing, because you can't guarantee the phase of when one cycle is going to be affecting the other cycle. So it's important to have a synchronization chain as part of that interface as well. And so that's another application of the synchronization chain. We are really primarily worried about in our exercises in this course about a single clock system with asynchronous inputs from the user. But it does have application in multi-clock systems, for later. So that's just something that I think is very, very interesting. That's all I have on this one. Basically, I just wanted to point out metastability, what it is, so you understand what it is, and also how to handle it in VHDL. It's good practice to use a dual chain like we've done here for your synchronization, for your synchronizing your asynchronous inputs. It will help ensure that you have a very, very high mean time before failure and make your design a little bit more robust. And it only consumes a couple of flip-flops, so it shouldn't be too big a deal in most FPGAs or CPLDs. All right, well, thanks for coming by and listening, and we'll see you guys next time in the next video. Thanks.